So I think when I talk, I should take the mask off, otherwise, not clear. Okay. I think when I talk, I should take the mask off. Maybe I need to also show the application. There is a picture there of the helicopter.
Yeah, we can follow you.
Okay, so I can show that one.
Yeah.
Okay. Morning.
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 Hi.
Hi.
I think if you're ready to get started, we will go ahead. Yeah, okay. So I'll just say good morning to everybody who's joined us on Zoom.
Okay. Yeah. So I think we can only run a little bit to see a little bit of it. So maybe you know, he need to run the machine, show you the motion. So we can see that first, and then I can explain later, right? Because he has another group that I have to take care of.
Okay. Sorry, folks. So welcome back into the fifth of our live lab walkthrough events. Today we're joined by Dr. Suong Hoa, Director of CONCOM, or the Concordia Center for Composites, and Professor in Mechanical, Industrial, and Aerospace Engineering. We're ready to roll, so I'm going to pass it over to Dr. Hoa right away to introduce himself and tell us about what he's working on in the lab. Over to you.
We start now?
Yeah, we can hear you on the microphone.
Yeah. Oh, okay. So what we are showing you here is a project on making the composite structures. So we work mainly with composite materials, which are the lightweight, high strength, high stiffness materials, and they are used in making many components in the transportation industry. So this is one example in the case where the composite are used to make the cross piece for the landing gear of the helicopter. So the process that we use here is by automation. I mean, we use an automated fiber placement machine to wrap the different layers of the composite over a mantle. And in this case, maybe I can show you the application. Maybe we need to go over there to show you the application. We can show here. So this is the piece that we want to do. So that is the cross piece for the landing gear of the helicopter. Right now it's made of aluminum, but aluminum have some kind of weakness in the sense that it may fatigue and plastic deformation. So the Bell helicopter would like to replace this piece using the composite materials. And so that's why we are working on the development of this particular piece. And so this, maybe you can show there. So this case here, that is we are now working on the straight piece. And that is, but later on, we also do that on the curved piece, okay? And so this one right now, we have a mantle that is made of aluminum, and then we are wrapping different layers of the composite on top. These are made of the fiber reinforced plastic composite materials. So I think that we can show you the process of the way how that is done. Normally, for most of the composite structures, people use it, do it by hand. But I think we enter into automation. So we have bought a machine. This is a robot in the sense that it has 7 degrees of freedom, and they can really wrap the composite around this particular piece. Okay. So I think this case probably Dr. Roska can run the machine so that you can look at that. But I think we need to, because of safety concern, we need to stay outside. Okay.
take up to 5 minutes to warm up.
Okay. So basically, so it takes a few minutes for the you need to use a torch, hot gas torch, and it heats up the piece of the composite that melted. You have the piece of composite going in, and then it wrapped around the mantle, and then it compact, melted, compact, and bond them together all at the same time. Are we on pause now? Are we running?
We're still going.
We're still running? Okay. So probably I can explain a little bit so that way that, that people know how to wait. Okay, so basically the composite came in a strip of 1/4 inch wide, and then it's like a ribbon. Okay, so what you do, you wrap the ribbon around a certain kind of mantle, which is the form that you want, and you have the ability to be able to change the orientation. In each of the ribbon, you have the fiber that is very strong and stiff. These are made of carbon material, which is a very strong and stiff material. So it's like a piece of tape that has a fiber in it, and you wrap with the ribbon and do different configuration. So by changing the orientation, we can design to meet the different loads that we have. So in this kind of design here, mainly we need to really, each layer of fiber has one orientation. So we have varied the orientation from layer to layer. And each layer has the thickness of a sheet of paper. Okay, so that means that we are wrapping probably about 30, 40 of the layers. And that could be sufficient in terms of to be able to provide the load support and the resistance against the different kind of the fatigue motion.
Do you have any of the material from?
Yes, we have the material. We can show. We have a piece of material. We have the.
Yeah.
Okay. Yeah. Thank you. So this one here is show you the piece of the tape. In the center, you have the. So you have the piece of tape here. It's about 1/4 inch wide. The width is informed. And you can see that it's black because it has carbon fiber in it. And the diameter of each fiber is about 7 micron. And you see our hair is 100 micron, the diameter of hair. This one is 7 micron. So it's tiny. You have a lot of fibers inside. And so basically what you do, we are wrapping this, and you see when you also need to melt. There is a resin, there is a thermoplastic. So that many layers will stick together by the time you wrap it. So that is basically the idea in terms of using the automation.
Where does this material come from? Who makes it?
We buy that from the United States, and also there are people in Japan, people in UK, United States, they make these materials. But in Canada, there's no facility to make it here. Okay, no. So
What is the name of the?
Sorry.
The name of this material?
This is the carbon pitch. Carbon pitch is the name of the thermoplastic. It's polyether ketone. So what you do, you get a lot of these kind of fibers, like say tiny fiber, and you run to a bath of melted. You melt this, and when it goes to the bath, the resin kind of coats the surface of the fiber, and the fiber gets stuck together. They get in that kind of a shape. And so the carbon pitch is a special kind of thermoplastic that has high temperature resistance, and also I can absorb good impact. So that is an aircraft kind of material that people have developed. So right now the machine. The machine has a hot gas torch. 900 degrees centigrade. It melts the thermoplastic. When it melts, then when many you have the presses against each other, it helps the structure. For example, we have made something like that. This one here is an example. Okay. Okay. So you have this one here is a similar kind of a tube that we have made of this similar kind of material. Now we have also made a rocket tube for the Space Concordia students. The Space Concordia, they are participating into the rocket. They want to shoot it up in space. So also we have used the same kind of machine and the same process to do that for them in the last several years. Okay, so that way you can tell the thickness is very thin, but it's very stiff and very strong. Similar kind of idea. Okay. So in yeah, we can start. Okay. Right. Yeah. Yeah, you can start. Yeah, he can start. You can. Yeah. Okay. So the machine is running. Maybe we can open the cage here. You can put it there. So that will be better than that. Okay, you can stand here and do that. Yeah, right.
Hey, folks in the lab, I wonder if you can hear me right now?
Yes, we can hear you.
So just letting you know, we're mostly spotlighting the iPad view because the camera is very unstable. And also, I'm not sure if Dr. Hoa is speaking right now, but we've lost sound.
No, we're not speaking at the moment.
Okay, you're not speaking at the moment. Okay, thank you.
But sometimes there is some kind of a defect. I think some kind of thing, so when it stops, we have to fix it.
And the bell tells you that there's
That's
been a mistake.
yes,
And then you
yes.
have to reset
Yeah, that's right,
the
yes,
tape.
right.
Okay.
So we have to cut some of that, and we have to start again.
Start, yeah.
So that is the roller, the roller sometimes has to be clean up, otherwise it gets stuck. So now we are wrapping at 90 degrees, relative to the axis of the, the axis of the curve, the thing here, we wrap 90 degrees. But we can also do that, say, 25 degrees, 45 degrees. So we have to run it all the way. So make that one layer, that layer 90 degrees, it's all the way.
All the way to the end.
That's right. And then the next layer, we vary the angle.
Rotate, change the angle.
The machine can do rotation. The machine can do different orientation. We can make another layer. So this strip here, we make 32 layers.
32 layers.
That's
Okay.
right, yeah.
Yep. Each layer is in a different orientation.
Well, the first 4 are 90,
Okay.
and the next 8, 25, plus minus 25.
Okay.
Okay, the next one 90, the next one plus minus 30. So the design,
Yeah.
we design in such a way that it can support the load and at the same time can elongate.
Would it be a good moment for me to start asking questions that are coming from the students?
So we have another lab where we do the testing.
Okay.
If you want to show that, do that, I can show that to you. as
Where
well.
is the
It's down there.
downstairs?
One floor down below.
Trying to go to the testing lab?
Sorry?
Do you want to go? Can we go to the testing lab?
Yeah, we can go. But this is the same motion. So if you
Okay.
don't want to do anymore, we can stop.
Let's
And-
go to the.
yeah, okay.
See if we can make it with our
Okay,
connection.
so okay. I think we finished. Yeah.
Hi, we're going to try to change location.
I think they finished. Yeah. Okay. Yeah. Okay. Sure. Okay. Okay. Yeah. Thanks.
And if you can hear me, you could spotlight the
Okay.
lab card, so just walk.
Right. Okay. Right. So
Switching location.
So this machine can do straight, can also do curve, and curve as well, because the shape of the piece is at the end is curve. It has some kind of curvature like this. So
The landing gear for a helicopter.
yes,
Do you do other types of? What are other applications?
yeah, we also do another project for Bombardier, and that is on the nacelle lip. The nacelle is the front part of the engine. So when you go to the airport, when you go, take a flight, normally under you see the airplane has a wing. Under the wing you have the engine, and the front of the engine is called the nacelle. It is a shiny part. You look at the airplane, you see kind of shiny, look like a donut. You know what I mean in terms of under the wing of the aircraft, you have the engine.
Yes.
And the front of the engine is the nacelle. That's where the air flow in. Air flows in. So right now it's made of aluminum, and also they want to change the composite. So we also are fabricating that using the same technology. The lab is here. So this is the testing lab.
Testing lab.
Yeah, right. Okay. So we have quite a few different kind of testing machines for different things. But you see, we have this structure. So we have this structure here. Okay. Put the tube, and it locks. Okay. Okay.
I think we might have lost the microphone. Can you hear us there?
Yes, we can hear you.
Okay. Okay. So also we built this machine from scratch in terms of trying to, because not many people have this kind of machine. And you have this frame here. Basically, it is this is the tube. See, this one we use this tube edges to hold the machine. Okay, and the machine have a load cell. The load is pushed down, and then it distributed into two parts. This part and this part here. So it's subject to 4-bond bending. We can do it with one bending like this, or you call it 3-bond bending, or here we have 4-bond bending. And we subject to the load, and we get the displacement. We put strain gauges on it to measure the deformation. So we have done quite a few. And you see, you have it's a whole bunch of tubes here. I don't know if you can see that. We have tested quite a few underneath. See a lot of tubes down below. I don't know. We can take out one to show you. Okay, one second. Maybe I go to the end here to pick up one piece. Some of the piece we cut up after we cut, we observe the end section. You see, we have some kind of damage or some kind of failure or not. See, we cut up, we can examine under the section to see what happens in terms of the manufacturing, to see whether there was good quality, there isn't a kind of a defect, something like that. Okay, so that's one thing you have. Yeah, you see when it fails, you have some kind of delamination. Maybe the other way you can see that here as well, right? You see the delamination, the crack that happened. When you take a look at that, where the camera can capture it, but you see the kind of failure, right? You see the inside. So that when you test fail, then you can get the load, you also the design and things like that. So that's the thing on the inside. Okay. And also during the test, you need to put this kind of a reinforcement. So that way, when you hit the loading point, when it loads, if you don't put the reinforcement on it, then it will fail early. It will fail early here. That's not a good test because we don't want it to fail here. We want it to fail somewhere here. That's why you have the clean part, where you have the understanding what the design is. Okay. So that means we want it to fail here and not here. So that's why we reinforce. We reinforce this part so that it doesn't fail here, because this is where the load is. Okay. So that's in terms of the way how we set up. Now we put a part. This is the fiberglass part to reinforce the location under the load, either under the load or at the support. Whenever you have some kind of concentration, that you need to reinforce so that it doesn't fail there. We want to make sure to fail in the clean part, where we understand what it is. What is it? We understand what it is so that we can really calculate and predict. Okay. So I think that's we have done about 10 different kind of tests on that in terms of trying to understand the effect of the different design and manufacturing onto the performance. We did another project. You asked us about this as well, and that is the similar to the same process, but this one here is for the tail boom, the tail of the helicopter. Okay, that was a previous project that was finished. And we say we are also testing that using this a different fixture in terms of the bending the bending or going motion this way. And this is the tube that we test. Okay, we did another project for Barry helicopter maybe several years ago. And size, you know, for the tail of the helicopter. And it's thinner and similar kind of manufacturing in terms of getting the robot.
We're seeing the sensors that are wired.
These are the gauges. These are strain gauges. They're tiny, very small, and they measure the deformation. They measure the local deformation down to thousands of portion. Okay, so we use it, and also you can see that the surface has speckle pattern. So the speckle pattern we use also using two cameras to capture it. We can get the difference in the deformation, and from there we can detect the relative motion in 3 dimensions. Okay. So
we have a lot of questions.
yes,
from our
yes,
audience
sure,
here.
sure, no
Can
problem.
we go maybe into the hallway where it's a bit quieter?
Yeah, maybe go in
Or
this room.
somewhere,
Yeah,
yes, and
yeah,
ask
yeah.
you
Okay,
some questions.
okay, here.
Anna, maybe you can,
Yeah, I think we have some other machine here, Autoclave, to be able to cure the composite and things like that. Yes, okay.
and setting up here. You can see who's here.
Can I start asking the first question?
I hope so, Joya. We'll just wait until we get confirmation.
Can you hear us?
Perfect.
Can you hear me?
Yes, yes, we can hear
Okay,
you.
you can go ahead with the question.
Okay, perfect. So the first question that our students were wondering is, how are your current research and findings influencing architecture, engineering, and also construction?
Architecture. Well, this is a product for the aircraft industry. Now, I don't know what you mean by architecture. Is that related to civil engineering, or is that just the design of the microstructure or the configuration of the product? Now, we did the design in the sense that you see the tube that we have, and the tube the tube has a thickness of about say 6 millimeters, okay, to be able to support the load. And each layer that is wrapped, that is around 0.1 millimeter. So that means if you want to have that kind of thickness, you need about 60 layers. And each of the layer has a different fiber orientation. For example, the first few layers wrap at, well, that'll be 90 degrees. And a few other layers that is wrapped at, say, 25 degrees. And then another few layers, 90 degrees, and the plus minus 35 or 90 degrees, plus minus 45. So if you talk about architecture, that means the arrangement of the fiber orientation, that's the way that it has been done. Now, this project we have been working on that since 2002, so 19 years, okay? So that means there's a lot of, at the beginning, we had to develop the so-called strain control design, the way how we designed it, by the stress or by the strain. So it took us some time to be able to design, came up with that kind of sequence. Sequence, I mean, in terms of the fiber orientation, 90 degrees plus minus 25, 90 degrees plus minus 35, 90 degrees plus minus 45. Because the way of this kind of structure is that they had to support the load, stiff and strong. At the same time, there's another requirement is that in the case of crash landing, in the case where you have some kind of a problem, that they should not break abruptly. Because if it breaks abruptly, then again, it will shock to the passenger. So we're going to have it fail gradually in terms of the gradual failure rather than sudden failure. So it requires a good kind of design in terms of the sequence of arrangement to be able to do that, to provide that kind of performance. So you talked about that design, and now the other question is, I don't remember what there are 3 parts in your question. They are first architecture, and the second is I don't remember now.
Yes, it was construction, but I think you very well answered this question. Maybe I'm going to jump to another one that the students had, which was, what are the recent innovations in the field of composites, and what are the corresponding emerging opportunities that you are seeing in your lab?
What the current trend right now is to go for automation, because the way that composite structure were made is mainly by hand. I mean, people will cut up the different kind of pieces, they lay it by hand on top of the mold, on top of the form. And so that has been done like that, but over the last 10 years, 15 years, there has a move toward automation. Now, the reason for that is because of the fact that people are using more and more composite in making airplanes. So for example, the Boeing 787 was not made a lot of composite before, but since 2007, they use more than 50%, 50% of the structure of the airplane is made of composite. So there's a lot of composite there. And also the plane is getting bigger in the sense that by using lightweight, you can save in the fuel consumption. You don't need to use a lot of fuel. And that way you can also make a bigger airplane. So bigger airplane, then again, you need, by hand doesn't make sense. In the sense you have people climbing on top of the whole structure of the plane lay down by hand. That doesn't seem to be working very well. So that's why there is automation. So right now there's a push toward automation the last 10, 15 years by major aircraft companies like Boeing, Airbus, and also Bombardier and Bell Helicopter, they also get into this field. And so we enter into this, we bought the machine, the automated fiber placement machine in 2012. So that was about 9 years ago, okay? And we are in right now at Concordia, we are the only university in Canada that have this machine. No other university in Canada have similar machine. Now, companies such as Bombardier, they have bigger machines, Bell Helicopter has a machine, but none other university has a machine. So we are ahead of the game in terms of this kind of technology. Worldwide, there may be about a dozen universities around the world that have this kind of technology. And we also initiated a series of the International Symposium on Automotive Composite Manufacturing in 2013. We were holding three consecutive symposia, one in 2013, 2015, 17, and 19. And so now the symposium is moved over worldwide. The next year, the people in University of Bristol in UK will host the 5th International Conference on Composite Manufacturing. So I think we are one of the leaders in this kind of technology right now.
Perfect. Thank you so much for your answer. Another student was wondering, because I think you mentioned that it was 19 years of evolving this project. And what would you say are the elements that changed the most throughout this process of developing this new material?
Well, when this project was introduced to us by the research manager at Bell, they only mentioned to us as what they want. They want to have a piece of the cross piece made of composite. They want to have lighter, stronger, stiffer, more performance. So that's what they say, but they don't know exactly how to do it. Okay, so we came into the picture and then we tried different kind of design. So the first student was 2002, 2006. We came up with the layup sequence, the strength control design. Okay, at that time we did not have a machine that can test. So we use the other machine, but the testing machine is not available. So after that, then we move into the manufacturer using a curve. You know, we were able to make a straight piece, okay, but the curve tube, very hard because of the fact you have the mantle. You need to have some kind of a thing that is strong and stiff to hold it. And you need to remove the mantle after. And removing for a curved structure takes a lot of time. So it takes another 4 or 5 years just to come up with a manufacturing technique to do a curved tube. Then after that, then came up with a testing fixture. We don't have any way how to test. So we spent the time to develop and test and install the testing fixture. After all of that is done, then we came up with the design. They told us it's fine, it's okay, but when make sure it absorb a lot of energy. You can really have the load, the deformation, but how much energy it can absorb. So right now we are working on getting the tube design in such a way it can absorb good energy. And so about 2 months ago, we came up with a design that satisfies their requirements. So we feel very happy about it. It took a lot of time. It's a long road right now, but I think finally we came up with something that satisfies and they seem to be happy.
Excellent. And I'm also wondering, so working on one project is very fascinating. So I'm wondering if someone would want to understand a day in your lab, what would you say are the proportions of testing, ideation, development? what would you say you were working the most on in these different tasks?
We do things all. We do things all at the same time. No, not at the same time, but whenever the needs arise. Okay, so depending on the stage of the project, they have different students. You have graduate students like PhD, master students, and also sometimes undergraduate students as well. And depending on the stage of the project, at the beginning, when we do simulation, load calculation, computer analysis, all of that, right? Then I think there is also the interest from the industrial partner. They have to be interested because they are the one that supply the funding. They have to give the funding, we apply to the government, get the money, combine that together. Then if they want to develop the prototype, then you have to come up with manufacturing. So we have to manufacture that. And then after that, they want to do more testing, we do the testing. So this particular project happened to be a series of many different kind of grants. At the beginning was the CRD grant, Collaborative Research Development Grant, a few of them. And then after that, there was the CRIAC, the Consortium of Aerospace in Quebec. They support a lot of money for that. And then after that is the industrial chair. So over this kind of series, depending on the interest, the success in getting the money and the definition. So it's difficult to say that, how many percent of kind of a testing, manufacturing, design, we don't really design it. We come with a need. If there's a need to do that, we do that. Okay, rather than say 25% design, 25%, it's not happening like that. It depends, whatever the need you do, you come up and put your effort along that direction to provide the answer.
Okay, perfect. Thank you. Also, so you said that Concordia was very innovative in the field. So where would you see your lab going in the next 5 years, let's say?
I have been at Concordia this year will be 44 years. Okay, that means I've been here for a long time. And that also at the same I have time to really develop a lot of equipment. When I first came here, nobody heard of composite, even myself. I didn't hear the composite myself. I mean, when I first came. And then I heard about it, so I started fresh. And then we developed one piece of equipment at a time. There was no lab, no space, nothing. I mean, the chair of the department told me at the time there's no space. So I obtained space piece by piece. When I apply for a machine, I got the machine here. Then I say, okay, I have the machine, give me the space. And that way I get the space that way. And this case, we developed the lab and that development. Now, in this case, over the last few years, we have recruited a few new professors coming in. So that way, then I'm now half load. So that way I'm going to be retiring fairly soon. And whatever, I mean, these new people coming in and now they're talking about artificial intelligence. It's the saying that we want to use the machine learning, artificial intelligence to really kind of predict for the manufacturing and also predict the behavior of the structure. They will continue doing the work on automation because automation is still very fresh, very new right now. But I think they move on more toward the kind of using artificial intelligence to be able to really do better in terms of prediction for the failure and also for manufacturing. That's what I see what these young guys are doing right now.
Okay, so jumping on what you just mentioned, so you mentioned the task that you need to predict the behavior of the structure when exposed to different elements or even the machines that you have in your lab. So would you say that when you are testing something, the results are predictable or even controlled, or it's always a surprise when you are testing your materials?
Well, I think the test that we do right now, we have method to be able to predict. We have calculation method to predict that. But again, these are the kind of testing conditions. I mean, you have control conditions. In the real application, you may not have control conditions. So that's why you need to have all of the other kind of facility to be able to do that. Okay, I mean, you have these kind of artificial intelligence to be able to handle a lot more variables. But in terms of the testing in the lab, yes, we can predict what we test. We have method to calculate and things like this. So we can provide that from the academic environment. But I think sometimes we want to really kind of do that in the real structure, in the case of the the real world applications, where there's a lot more variation than that. And that's why you need to have the actual method to come in to help you to do that.
Okay, perfect. And I think the last question I'll ask is, would you be able to introduce the machine that is behind you, the blue one?
Yeah, this machine is called an autoclave. Now, an autoclave is basically an oven with pressure. Okay, so the case of the curing or the case of manufacturer composite, you need to have both heat and pressure. So this machine here has a cylindrical shape. You see the shape is round. And that is important to be able to contain the pressure. Because if you don't have a round shape like that, you cannot contain high pressure. So this machine, we bought that maybe 15 years ago, and it can handle, it can be used to manufacture either thermoset matrix composite or thermoplastic matrix composite. It can go to 100 psi pressure. The temperature can go to 500 degrees centigrade. So, so it's a very useful machine. Again, I think that we are one of the one of the few, maybe 2 or 3 universities in Canada having this kind of machine. So in the sense at Concordia, we have a lot of facilities for manufacturing. So I'm offering a course, manufacturer composite, to students, and their students from all those places come here to take the course. Polytechnic, Sherbrooke, McGill, and there's a lot of people because they don't have as much facilities that we have here in terms of manufacturing composite.
Well, I think you make us very proud to attend Concordia University. So thank you so much for having us in your lab. And I'm not sure if students have any questions, but if ever there's something else you want to show us in your lab,
Sure.
You're welcome to.
So I mean, I'm available, and then like I say, I give the course. I give the course of manufacturing composite every year. So the course is going on right now. So students are welcome to come to take the course if they wish to know more. But
Okay.
you know, we are here anytime anybody wishes to ask a question. So thank you very much for this opportunity
Perfect.
to show our facilities.
Thank you so much to you.
Yes,
you.
indeed. Thank you. We got to see 2 lab spaces. Thanks everybody for being here and joining us. We're seeing some thanks in the chat. And of course, we've been streaming this live lab walk, so it's available for others to watch later. And I'll send you the link as well, Dr. Hoa. So thanks again for your time and meeting us early morning today. And we'll see you all for the next episode. So thanks for being here. We're going to close up now. Bye-bye.